Hi everyone, welcome back to the Vanderbilt Institute of Nanoscale Science and Engineering. This week we are in the VINSE cleanroom to put together the fabrication steps we talked about in the other videos. We will use deposition, etching, and photolithography to fabricate a graphene field effect transistor. So, what is a graphene field effect transistor? Well, graphene is a two-dimensional sheet of carbon atoms. Due to its unique sp2 type bonding, graphene is a semimetal that shows interesting optical and electrical properties. It is transparent and an exceptional conductor of heat and electricity. A transistor is a semiconductor device used to amplify or switch electronic signals. It is composed of semiconductor material with 3 terminals and is connected to an external circuit. A voltage or current applied to one terminal, the gate, controls the current through another pair of terminals, the source and drain. A field effect transistor uses an electric field at the gate to control the flow of current rather than directly injecting current at the gate. Metal oxide semiconductor field effect transistors, or MOSFETs, are the dominant semiconductor device in integrated circuits and typically use silicon as the semiconducting material. Because of its attractive electronic properties, graphene has been suggested as an alternative to silicon in transistors. However, as it is a semimetal and not a semiconductor, graphene's use in traditional transistor applications has been limited so far. The off state is not off enough for it to act as a MOSFET transistor would in an integrated circuit. Nonetheless, graphene field effect transistors are superior to silicon in other applications. For example, they can act as exceptionally sensitive detectors for medical diagnostics, environmental monitoring, and bioresearch. In this video, we're going to make a graphene field effect transistor using deposition, lithography, and etching. First, we need some graphene. While this can be made by exfoliating graphite down to a single layer, in this case, we need a relatively large sheet, so that we will use a low-pressure chemical vapor deposition process. Methane, CH4, and hydrogen, H2, flow into a quartz tube heated to 1000 degrees C. Inside the tube is a clean copper substrate. The copper acts as a catalyst for the decomposition of CH4 to its component atoms, carbon and hydrogen, and the carbon atoms bind together to form graphene. By adjusting the flow rate of the gases, the pressure and temperature in the tube, and the reaction time, we can ensure monolayer graphene is formed. Higher quality sheets can be grown by rapidly cooling the copper substrate after growth. To do this, we use a magnetic boat to remove the copper from the hot zone of the furnace immediately after the reaction is complete without opening the system. Graphene must be grown on copper to catalyze the reaction. However, this is not a good substrate for most applications. For example, we need the graphene to be electrically isolated by an insulating layer to make a field effect transistor. In this case, our desired substrate is SiO2 on silicon. This provides us with an insulating surface on which to fabricate our device. We also use a very specific SiO2 thickness, 300 nanometers. This layer thickness allows us to visualize two-dimensional materials using an optical microscope. To move the graphene from the copper to the silicon substrate, we use a polymer support. Polymethyl methacrylate, PMMA, is drop cast onto the copper substrate and baked on a hot plate to remove the excess solvent. After the PMMA is dry, we float the copper substrate on a bath of copper etchant. Copper etchant is a solution of iron chloride, which reacts with copper to form the soluble product copper chloride. After 30 minutes, the copper has completely etched away, leaving behind some graphene on PMMA. We wash the graphene in water baths to remove the iron chloride residue. Then use a silicon substrate to remove the PMMA from the final bath. The sample is then placed at an angle on a hot plate to dry, then bakes close to the glass transition point for PMMA to ensure good contact between the graphene and the substrate. Finally, the sample is placed in NMP overnight to remove the PMMA transfer layer. Now that we have our graphene layer, we need to add source and drain electrodes. To do this, we will pattern a chrome gold layer using a liftoff process. The first step in this process is photolithography. We spin coat a negative photoresist on the sample, bake it to remove the excess solvent, place it into the mask aligner under a photomask, then expose it to UV light. A second post-bake provides the thermal energy for the negative photoresist to finish cross-linking. Then we remove the unexposed photoresist using basic developer solution. The parts of the photomask that we want to metallize are opaque and thus free of photoresist. The rest of the sample is covered with photoresist. Next, we use physical vapor deposition to deposit our metallic electrodes. Resistive evaporation is used to deposit a 5 nanometer layer of chromium onto the sample to promote adhesion between the graphene and the gold. Then, 100 nanometers of gold is deposited using electron beam evaporation. Gold is chosen as it is an excellent conductor and unreactive, so it is not susceptible to oxidation in the following process steps. When deposition is complete, the photoresist is removed to leave behind the patterned gold electrodes using liftoff. Acetone, or NMP, N-methyl-2-peroxidone, is used to dissolve the photoresist. The negative photoresist is thicker than the metal layer and has an undercut, meaning the photoresist overhangs the substrate. The gap formed between the edge of the photoresist and the metal film on the substrate due to this overhang means that the solvent can easily reach the photoresist to remove it. Our sample now has a graphene layer and patterned source and drain electrodes. Now we must remove the excess graphene to prevent our devices from being in electrical contact with each other. To protect the graphene we want to keep, we perform another photolithography step, this time using positive photoresist. Positive resist is spun onto the sample, then baked to remove excess solvent and placed into the mask aligner. We want to keep a small bar of graphene under the ends of the gold electrodes, so we must perform an alignment between the mask and the electrode pattern on the sample. This ensures protected graphene is at the center of the electrode pattern. To do this, we use an optical microscope and alignment marks on the substrate in the photomask. Once the substrate and the mask are aligned, we bring them into contact, then expose the sample. The exposed positive resist is removed using a basic developer solution. A small bar of unexposed photoresist remains, which protects the graphene between the electrode ends at the center of the pattern. A reactive ion etch is used to remove the uncovered graphene. O2 plasma is selected as it reacts chemically with carbon. While this etch will also remove photoresist, which is carbon-based, the graphene layer is only a single atom thick, much thinner than the resist layer at 500 nanometers, so selectivity is not an issue in this case. The process is short at 30 seconds, and parameters are selected to ensure the etch rate is low, as there is not much material to be removed. Finally, we must remove the photoresist from the remaining graphene so it can be contacted electrically and/or functionalized for use in sensing applications. To do this, we again place the device in a bath of acetone or NMP. Once the resist is removed, the device is rinsed with acetone and IPA, then blown dry. Now it is ready for characterization. Scanning electron microscopy, or SEM, is used to image the device. This allows us to verify the graphene and electrodes are the expected size and shape, the chemical composition of the system is as expected, and identify the number of layers in the graphene sheet. Raman spectroscopy can also be used to identify the thickness of a graphene sheet. We can use the Raman microscope, one of the characterization instruments in the VINSE analytical lab, to measure the spectrum of graphene. Raman identifies the vibrational modes of a material. For graphene, there are 3 key peaks which correspond to 2D, G, and D vibrational modes. The G peak is an in-plane vibrational mode, while D is the breathing ring mode. The D band is only active if the graphene has defects present, while its second order mode, 2D, is always present. The ratio between the 2D and G peaks can be used to determine the number of layers of the graphene sheet, with monolayers having a 2-to-1 ratio of intensities between the 2D and G peaks. Finally, we must make sure our transistor works. To do so, we perform a current voltage, or IV, measurement. This device can be measured by making contact with two electrodes on the top side, the source and drain, and using either the back of the sample as the gate or dropping a liquid electrolyte on top of the device to use as a gate dielectric. We expect to see high current through the source and drain when the gate voltage is high, and low current at low gate voltage. This results in a U or V-shaped IV curve. Graphene field effect transistors are one of many different devices fabricated inside the VINSE cleanroom. While they all have different applications, most devices are constructed using the same three processes: lithography, deposition, and etching.
Hi, my name is Alberto. I am a graduate student in the Lee Lab at Vanderbilt University. I use the VINSE cleanroom to fabricate retina-on-a-chip devices, which are microelectromechanical systems using lithography, deposition, etching of the materials polyimide, gold, SU8, and PDMS. These have applications to study the neuron connections in retina, which will help us understand better how intracellular communication works.
Hi, my name is Fabian. I'm a graduate student in the Valentine Lab here at Vanderbilt. I use the VINSE cleanroom to fabricate tunable metal surfaces. My devices are made using lithography, deposition, and etching of silicon, silver, and graphene. The functions of my device is essentially to move the absorption spectrum across the visible wavelengths of light, and these have applications in nanophotonics and in biomimetics.
In the VINSE cleanroom, we fabricate numerous different devices using three simple steps: lithography, deposition, and etching. The fabricated devices can then be characterized using tools in the cleanroom, imaging suite, and analytical lab. A full list of the tools available for these processes can be found on the VINSE website at vu.edu/VINSE. These devices are incorporated into research projects across campus, from diagnostics to metamaterials. Join us in the VINSE facilities to build and characterize your own.